maximization. In this particular segment, we want to look at product mix decision, where we've got two or more constraints. In this case, we're going to use what we call linear programming. You find because the constraints are not giving us the same ranking, we cannot use the contribution per limiting factor. So the next best method is linear programming. Now, so this is where you've got the constraints are not acting in the same direction, and so the rankings are different. And we're going to use the tools, the linear programming, obviously, to calculate the optimal production mix, as well as shadow price, which are opportunity costs. So when we talk about what is linear programming, I think from mathematics, you guys remember this technique, which is used to allocate resources between two products to maximize contribution. And we use it where you've got more than one constraint and where there are two products, because it sits on an X and Y axis, so you can only do it for two products. The objective function is to maximize contribution. Remember, contribution minus fixed cost is profit. In this case, we are not concerned with fixed costs because they're not going to change the decision that we're making. So we look at maximization of contribution. So step number one, determine the objective function, which is the function, the contribution function that maximizes your profit. Number two, identify and specify the constraints that you have in the process. Then compute the optimal solution using the graphical approach. So you draw a line diagram for each constraint, label each line. We're going to go through this process. Draw an arrow for each line to show whether the cost should have been above or below, and use the objective function to identify points on the diagram where contribution is maximized. Then identify the two constraints which intersect at this point, and then use a simultaneous equation to solve. Use X and Y values in objective function to find the total maximum contribution. Now, the best way to look at this is to look at an example. So I've got this example that we want to go through. I've got product Y and product Z. There's the standard selling price. We've got materials, which is 8 units at $4, 4 units at $4. All that giving us a contribution of 16, or 14 and 16. And then we are told that there's labor, which is only available 2,800 hours. We've got constraints in materials. We've also got constraints in machine hours. Right, so I want to demonstrate how you'd approach this question that we have in the process. So number one, based on our steps, we said let's determine what is the objective function. So the objective function, which is the point in which you maximize contribution, is equals to our contribution for Y. It will be contribution of Y times the number of units that we're going to produce under Y. We add plus 16Z. So this is our objective function. Do this and you already have 1 mark. So this is very easy. Now we want to determine the equation for the constraints. So the first one is, let's start with material. And we'll say material, we need 8 units of material, which is at $4 a unit. So for our, based on the material that we're going to use in the process, it's 8Y of material plus 4 units, which we need for 1 unit of Z. This should be greater, or rather, whatever material that we use should be less than or equal to 3,440. That's the material function. Then we do the same for your labor function. In this case, we're told that 8 hours at 60 per hour, and then you've got 6 hours at $60 an hour, and 8 hours at $80, and with a total cost of $80. So you do the same for labor. It will be 6Y plus 8Z is less than or equal to, for labor it's 2880. You do the same for machine hours. I think now you've gotten the hang of it. 6Y plus, in this case it's 6Z. It's less than or equal to in this case 27660. Then the last one, the marketing manager estimated that the maximum sales potential product Y is 420. So whatever we do, Y should not exceed 420 units. So it becomes 420 should be less than 420 Y. In this case, we're saying Y should be, so it should be Y should be less than or equal to 420. That's how you come up with the different equations that you're going to use to solve this. So after I've come up with the equations, I'll end up with a graph like this. There's the Y is less than or equal to 420. Then I've got the one that's for labor, I've got the one that is for material, and I've got the one that is for the machine hours. So this is the area that is common to all the graphs. So this is the area that we need. So the potential combination would be point A, point B, point C, and point D. This is the potential points in which production is maximized. So let's find out, how do you find the actual point in which production is maximized? Right. Now, the optimal point, so we're saying any point in the physical area that represents mixed combination that meet the constraints. However, we want to determine the maximum contribution. So what you do is get the slope of the objective function and place on the diagram. So the objective function, like we have said, is 14y minus plus 16z. Therefore, we solve for y, because we want to calculate the gradient. In this case, it's minus 16 over 14. Now, you find that our gradient is negative, so you need to be able to look at only points that give you a negative gradient. At a point in which they touch leaving the feasible area, that is your optimal point. In this case, if you go back to our diagram, it will be at point C. So these are the two lines that have got a negative gradient. This one is already eliminated because it's outside our area. So it's only these two lines, which is F and C. And at this point where these two lines meet, that is where our objective function is going to be. And at this point, you solve these two equations which intersect at this line simultaneously, and you can get the maximum contribution mix that you need to maximize profit. So in this case, based on my calculations, when I took these two constraints, it's Y 400 and Z 60. So the total contribution that we get in this case is 6560. Now, just some points. It's in an exam, just be able to draw a graph in a not very complex graph. We're not going to give you a graph paper, but just be able to draw something that represents the graph. I want to finish off this lecture by looking at chart of prices, which represents the opportunity cost, but in a different way. Now, when you talk about opportunity cost, we're talking about how much if we're going to give up 1 unit of how much would it cost us to be able to give up 1 unit. But shadow price would take how much would you want to pay for an additional unit. In this case, we're saying labor is a constraint. If someone is going to give us labor at a higher price than our normal rate, how much more would we be willing to pay for that labor? Remember, if we get that labor, it's going to increase our production. And in that process, how much more should we be able to pay for the labor? Now, when you look at shadow prices, let's say we're talking about for materials. We've got an object, this is the function for materials, and we say if we're going to get 1 additional unit of material, it becomes 3441. Then you solve this equation based on 3441. When you've solved this, you would find that Y can be increased to 400.2 and Z would need to come down to 59.58. So that becomes the new optimal production mix if we're going to get 1 additional material. Then you can calculate how much contribution would that give us. So there's a change in this case of 0.4 contribution. So the shadow price, the plant output will increase by 0.2 and for Z reduced by 0.15. and the total contribution would increase by 0.4, which is the shadow price. So what 0.4 means is, if someone is going to bring an additional material to us, the maximum price we can accept for that is 0.4. If the price goes above 0.4, it means our contribution is going to increase. But as long as the price for an additional unit of material is below 0.4, we can be rest assured that we'll get an additional increase in contribution. Right, I think these are other methods. In conclusion, these are the different methods that you need to know when you're calculating in constraint optimization. It's a very favorite subject when it comes to examination, so please be well prepared. Thank you.